This is a 1-hour introduction to TMS 403, Direct Design Handbook for Masonry Structures. This handbook provides a step-by-step method of designing single-story concrete masonry structures. The method provides tables of pre-qualified designs so that minimal calculation is required. The method is direct in that it takes you from what you know to what you need to know. Although this is a structural engineering standard, it is laid out so that virtually anyone in the construction industry should be able to use it. TMS 403 is a quick and easy method of providing safe and economical designs. These designs are fully compliant with the strength design provisions of TMS 402, building code requirements for masonry structures. This document is developed by the MSJC, the Masonry Standards Joint Committee, which is sponsored by the Masonry Society, the American Concrete Institute, and the Structural Engineering Institute of the American Society for Civil Engineers. The 2012 International Building Code and the 2012 International Residential Code, that's the IBC and the IRC, both permit TMS 403 to be used as an alternative to the MSJC standard. These standards can be purchased from the Masonry Society, TMS. TMS is an organization of architects, engineers, contractors, professors, manufacturers, and building officials, and others dedicated to the advancement of knowledge on masonry. My name is Ben Harris. I'm a structural engineer with CHA, a national, multidiscipline, full-service engineering firm with over 25 offices across the country. I'm also the chair of the TMS Design Practices Committee, responsible for the development and the maintenance of TMS 403. There will be two presenters after me. The first will be Jason Thompson. Jason is the Director of Engineering for the National Concrete Masonry Association, NCMA. NCMA is an international trade association for the concrete masonry industry. Jason is also the Secretary of the TMS Design Practices Committee. After Jason, you will see Dr. Rich Klingner. Rich is a professor of structural engineering at the University of Texas at Austin. Rich was also the chair of the MSJC standard on which TMS 403 is based. In addition, Rich is a voting member of the TMS Design Practices Committee. I'll discuss the scope of the document. Jason will address the conditions when and where and other limitations which are required for use of TMS 403. And Rich will discuss the direct design procedure and give a design example. And after all that, I'll wrap up the presentation for that hour. The scope of TMS 403 is to provide a direct design procedure for the design of single-story concrete masonry structures. The method covers design of both reinforced and unreinforced masonry. For any design, you must account for several things. For example, gravity loads, such as the dead load of the structure, the live load of occupants on top of a roof, as well as snow load, all of which transfers the load vertically into the ends of the joists into the wall system. You must also account for lateral loads, such as wind forces and seismic loads that shake a structure. Both of these cause some walls to bend into and away from a structure and cause other walls to act as shear walls. One must also account for the effect of openings in resisting gravity loads and lateral loads. This is to create a load path, a series of elements creating a chain between the point of load application and the foundation which ultimately has to resist those loads. All of this should be done so that there is sufficient resistance in the design of the masonry elements to resist the loads along that load path. And those resistances and loads must be calculated in a method that's compliant with applicable governing building codes, such as the International Building Code, ASCE 7, which is the document regarding design loads, and the MSJC standard shown here. Furthermore, it's good practice to use good judgment based on experience. And you see here the TMS Masonry Designer's Guide, which is an excellent reference on proper specification of units and design of masonry so that it is constructible and economical. All of these important things are behind the direct design tables. The objective of the TMS 403 committee during development was to eliminate as much as possible any unnecessary intermediate calculation. There are some tables in TMS 403 where a single value is literally the result of thousands of calculations. The format of the tables is also laid out so that the input is information that one has readily available at their fingertips, and the output is information that has a real-world meaning, such as the spacing of vertical bars, or whether or not an unreinforced option is permitted for that application. ASCE 7 requires a rather complex load analysis to determine the snow load on top of a roof. The tables are structured so that when a user is going through the method, one does not need all of the load information. One only needs what is found on a mapped value of ground snow loads. In addition, for wind loads, in a similar fashion, ASCE 7 requires an even more complex load analysis to be performed to determine wind speeds and to determine wind pressures, which actually will vary depending on the tributary area of a particular element. Rather than have the users go through this complex analysis, with direct design, one only needs the mapped wind speed value. Given the location, one can determine the basic wind speed and use the direct design tables to design for wind. And in a similar fashion, for seismic analysis, one refers to two maps which provide the short-term and long-term accelerations respectively, SS and S1 values, from the maps. So that this is possible, the committee, the Design Practices Committee, had to define a finite set of circumstances to perform these analyses. One calculates the cumulative length of shear wall segments required along a line of shear walls for a diaphragm by using two very simple equations that are based on coefficients K1 and K2 that are given as output using the method. The way that this is possible is only by defining a finite set of circumstances so that there is a finite number of analyses. This is possible only because parameters are limited in which TMS 403 may be used. In addition, options are dictated by the method with regard to designs that are pre-approved. Therefore, the method gives you final, reliable designs. Because the parameters are limited, it's possible that a particular application will not be you will not be able to use TMS 403 for a particular application. In that case, one can use the MSJC standard. It's also possible that because the design options are dictated, that one may desire a smaller bar spacing or a different type of unit or another configuration, in which case, again, the MSJC standard could be used. It's important also to note that the Design Practices Committee, in developing the document, chose not to do a worst-case design for the entire country as one set of problems. So as to make the method more economical, families of generally similar conditions were analyzed and output is given for those families. Therefore, the Masonry Standards Joint Committee document could be used for a particular application to determine a slightly more economical design because the document is based on the worst case of each family of conditions. The document, however, it should be noted that the document can be used for all of these cases for preliminary design purposes and for partial design purposes. The commentary of TMS 403 describes the rationale behind each step of the direct design method. If one understands the rationale, one can use the method unofficially to perform the design steps that are applicable and do custom designs for only the required steps. In addition, partial designs can be performed because TMS 403 permits that certain elements of a structure be designed by another method that's approved. There are many potential users for this document. Architects can use TMS 403 for initial floor plans and for developing preliminary elevations. Structural engineering firms can use this handbook in delegating simple designs of simpler structures or simpler portions of structures to younger engineers that are productive at a lower rate and also learning on the job to get a feel for what is good practice. Structural engineering firms can also use this document to identify areas which are not permitted by TMS 403 that may require more focus, a more custom design, spending more time where appropriate. Contractors can use this method for preparing preliminary cost estimates, for interpreting plans, value engineering, and also during construction when faced with challenges, contractors can use this method to develop proposals independently to take to the design team and owners. Building officials and plan checkers can use TMS 403 so as to screen projects and identify designs which perhaps appear significantly less conservative than TMS 403, possibly deserving a more detailed review. Masons, suppliers, and manufacturers can use this document to possibly identify designers that may be consistently more conservative or less conservative than TMS 403, in which case TMS 403 may provide an opportunity for dialogue with those designers about design practices. And finally, professors can use this document to educate university students in the basic process required to design a structure, specifically a masonry structure. TMS 403 was specifically written for all of these potential users. Now, Jason will summarize when and where and under what conditions TMS 403 may be used.
Greetings, I'm Jason Thompson, and as Ben had just outlined for us, there's a number of applications in which the direct design method was really tailored to apply to. And as we looked through identifying all the different applications and requirements that the building code stipulate in terms of structural design requirements for masonry, there's a number that we had to kind of go through and strip out in terms of making the process very simple, very applicable, and very direct in terms of its application and use. Specific applications in terms of how the direct design method is laid out. They do limit site conditions, they limit architectural configurations for structures, and they do limit loads in terms of how they are applied and what magnitudes they are. In terms of the specific requirements for site conditions, as Ben had mentioned, there are ground snow load requirements that cannot exceed a maximum value of 60 pounds per square foot. Now these are the ground mapped snow load values, not the snow loads that are applied to the top of the roof of the structure. These may vary depending upon the configuration, the slope of the structure, and whether or not there's parapets that could cause drifting. All these variables were taken into consideration when developing the design tables of the Direct Design Handbook. The next site condition is wind speed requirements. The maximum mapped basic wind speed in accordance with the 2005 edition of the ASCE 7 document is 150 miles per hour. Now this was captured and applies to all geographical regions of the U.S., including the hurricane-prone regions of the U.S., that have a mapped basic wind speed of 150 miles per hour or less. These structures could be designed using the Direct Design Handbook. And also the mapped spectral seismic accelerations cannot exceed 3G for short period spectral accelerations and cannot exceed 1.25 G for 1 second spectral accelerations. This is intended to really capture the vast majority of the United States out there. There are some areas where these values could be potentially exceeded. For example, in the area surrounding the Great Lakes, in the upper northern Wisconsin, Michigan, and Minnesota areas, as well as the coastal region of Maine, the mapped ground snow load values are too high to apply to use the direct design method. In terms of seismic loads, the New Madrid area, the fault zone around the New Madrid area, does have seismic accelerations that could exceed the limitations imposed by the direct design method. And in terms of the Florida Keys, the mapped basic wind speeds around the Florida Keys area and the very southern tip of Florida do have wind speeds that are too great for application of the direct design method. Now, in addition to these values that are in that are stipulated by the handbook and dictated by the International Building Code, there may be special regions of the country that may have, by ordinance, ground snow loads and or wind speeds that are greater than what's dictated by the building codes out there. The next limitation is in terms of the loading requirements that the direct design method stipulates. And again, in order to make the entire process very simple, very applicable to a lot of different structures out there, there are some constraints that are applied in terms of the different types of loads as well as how those loads are applied to the structure. In developing the pre-engineered design tables of the direct design method, the types in application to the types of magnitudes and loads that were considered were roof live loads, roof dead loads, snow loads, wind loads, seismic loads, rain loads, and ice loads. The latter of these were all prescribed by the International Building Code and or ASCE 7. The dead loads for the roof, however, are a design variable that could change depending upon the application and the structure. In our case, we have, for the Direct Design Handbook, the dead load can start to drive different designs in terms of its magnitude and how it's applied to those walls out there. The maximum value for roof dead loads considered by the Direct Design Handbook cannot exceed 30 pounds per square foot. The minimum design value for roof dead loads cannot be less than 2 pounds per square foot. This range is necessary in terms of being able to consider whether or not those dead loads are cumulative to a certain design event. For example, the roof dead load would be considered the maximum value permitted by the handbook in developing those tables where it would contribute to a particular design event, such as in the case of the axial load on a wall. The roof dead load was considered to be minimum in situations where the roof dead load would offset a certain particular design event, such as the case of axial tension or roof uplift due to wind. In addition, certain structural configurations can start to change how different loads and how those loads are applied to different types of structures. In order to maintain a certain limitation in terms of the number of variables that were considered within the Direct Design Handbook, we did need to constrain the number of different architectural configurations for different structures out there. As Ben had mentioned before, the Direct Design Handbook applies only to single-story concrete masonry structures. Roof pitches can vary anywhere from nearly flat all the way up to a 12-12 pitch roof. All diaphragms, the roofing system for these structures, must be rectangular. That would preclude the use of any kind of radial or circumferential walls around structures that are used as a load-bearing or shear wall type of element. The maximum diaphragm dimension in any one planned dimension cannot exceed 200 feet. A different way of saying this is that the spacing of the shear walls in any planned dimension cannot exceed 200 feet. In any situation where this dimension is exceeded, then subdiaphragms need to be incorporated and shear walls need to be incorporated between those intermediate shear walls to keep this maximum dimension limit constrained. The maximum joist space or maximum joist span must be less than or equal to 60 feet. In situations where the planned dimensions of a structure are greater than 60 feet, you need to incorporate internal columns within that structure. The next set of limitations apply more to how that structure is put together, the types of materials that are used in the construction of that structure itself. In terms of the roofing system itself, the Direct Design Handbook permits virtually any type of construction material to be used. However, it does dictate that the roofing system or the diaphragms be flexible as defined within the building code. And this was, again, to try to limit the way and how the different loads were distributed throughout the lateral force resisting system. All construction must consist of 8-inch concrete masonry laid in running bond construction. And again, as part of just one of the limitations and simplifications of the direct design method, by maintaining simply just this one wall thickness and this one bond type, it created a much simpler set of tables for the end user to apply to. Now, oftentimes people will look at this 8-inch wall thickness as a constraint or a limitation that precludes the use of this handbook for a number of different structures out there. But as one becomes much more familiar with the handbook, you'll see that there's many applications out there where 20 and even 30-foot tall walls can be used in vast areas of the country using 8-inch thick walls or 8-inch thick construction. The handbook does require the use of type S mortar, and this could include Portland cement lime mortar, masonry cement mortar, or mortar cement mortar. In higher seismic design categories, there are some building code imposed limitations that are carried through in the Direct Design Handbook that apply to Aaron-trained Portland cement mortar and masonry cement mortars. And again, as a simplification, all the reinforcing steel that's used for out-of-plane bending, for in-plane shear, and other types of primary, lateral, and axial loads must be number 5 rebars. The one exception to this is in the situation where a designer opts to use stirrups in lintels designed in accordance with the handbook, the stirrups could be number 3 bars. So as we look at all the different applications that the direct design method could be applied to, one of the things that does start to jump out quite readily is that with all these different constraints and these limitations that's supposed, how many different structures could potentially be used to design using the Direct Design Handbook. One of the primary motivations behind the committee in developing this thing is that it needed to have a broad application, not just geographically, but to a number of different structures out there. And in doing so, and in developing a lot of these tables, they developed a section that addresses specific modifications to the handbook itself to allow it to be applied to a much broader cross-section of different structures out there. There are many different situations that, whether they're architectural, potentially loading, configuration of structures, those types of things, that may or may not kick a certain structure out of the limitations of the Direct Design Handbook. That in itself doesn't necessarily mean that the handbook cannot be used to design that structure. It simply means that portions of it need to be modified, or specifically, sections of that structure that don't comply with the limitations imposed by the Direct Design Handbook be designed using more conventional engineering techniques, and the rest of the structure itself be designed using the handbook. So as you look at a number of different applications that could be potentially designed using the Direct Design Handbook, the first one that obviously comes to mind is relatively simple warehouse rectangular boxy types of structures. This is kind of the genesis of behind developing much of the Direct Design Handbook. Is there's a number of structures out there. They're very regular, they're very simple structures, but the design process behind them does take a fair amount of effort. So if we can simplify the design process, apply it through the Direct Design Handbook, and apply it to these types of structures, we can save in terms of not only the design time, the layout time, the construction time in the end. But as the Direct Design Handbook really started to take form, we started to see that it could be applied to a number of different structures out there as well. We can start to look at more complex structures, such as school structures out there, where the architectural features and the layout of the structure really can vary quite significantly, but it still falls within the limitations of the Direct Design Handbook itself. We can even look at more larger complex types of structures. Strip malls are another natural for direct design. Although many strip malls have dimensions that are greater than the diaphragm limitations of the Direct Design Handbook of 200 feet, you can incorporate a number of just adjacent diaphragms and build ultimately a strip mall that has unlimited size and plan dimension based upon the Direct Design Handbook by incorporating and breaking that entire complex up into substructures or subdiaphragms with concurrent shear walls. And finally, ultimately you can, once familiarity is gained with that Direct Design Handbook, really start to design much more complex structures that have significant variations not only in the configuration and their application, but ultimately in how they're applied and constructed. So with that, next is Richard Klinger, University of Texas at Austin. It's actually going to provide a design example for us using the Direct Design Handbook.
It's really a pleasure to be with you to follow up on the information that my colleagues Ben and Jason have shared with you about the direct design method. I'm Richard Klinger of the University of Texas at Austin, and I'm going to be going through a sample application with you. Let's look at the most important points from this presentation. The direct design method is a simple way to design many masonry buildings. It focuses on a basic layout of reinforcement. It addresses the same things that a designer would ordinarily consider in a very step-by-step way using tables. Okay. Let's start off and talk about box-type structures, how they behave. We're going to look at a starting point for design. We're going to see how boxes are combinations of vertical strips in walls that are oriented perpendicular to a direction of lateral load, and then walls parallel to the direction of lateral load. We're also going to talk about the design of lintels, the masonry that overlies openings, and we're going to look at simplified analysis for lateral loads, and finally, design of diaphragms and detailing. And what I want you to keep thinking about as we go through these steps is that the direct design method is doing all this for us. Okay? We're looking, as we use the direct design method, at a simplified flow and at tables. And behind those tables, transparent to the user, is a bunch of very good calculation, okay, and a condensation of the results of that calculation in designer-friendly form. So let's look, please, at this structure. It has no beams or columns. It's a box. It has vertical reinforcement at corners, jambs, and regular intervals elsewhere. It has horizontal reinforcement in what we call a bond beam at the top, where the walls and the diaphragm connect. It has horizontal reinforcement above openings. And let's look again at that diaphragm, because there's a couple things that are important. First one is, you can see the arrow that goes from left to right on the diaphragm, and it indicates the direction of span. Some of the walls will resist gravity loads, vertical loads, from their self-weight only. Those are non-bearing walls. The walls on the front and back of this particular building are such walls. They're non-bearing. The walls on the left and the right will also take loads from the roof, and we call those bearing walls. The reason that this distinction is important is that the bearing walls will have greater axial loads, usually in compression, and while self-weight is always applied through the midplane of the wall, gravity loads on bearing walls can be applied eccentrically to the midplane of the wall, and so they'll tend to give us bending moments. The walls resist gravity loads through combinations of axial force and moment. That's what they're going to be designed for. Non-bearing walls will resist concentric axial load, and bearing walls possibly eccentric axial load. What's really important about the picture you're looking at now is that it's an idealization. It's a simplification of how this box-type structure resists load. We know that if we were to do a finite element analysis of this building, we'd have bending moments going in two directions in all of the walls. They really act like like slabs in a vertical plane. But we can simplify that for design. The gray strip that you can see that goes from the level of the foundation to the level of the roof diaphragm, that can be idealized or simplified as a simply supported strip that takes loads that are applied perpendicular to the screen that you're looking at. Those loads are transferred in the form of reactions to a foundation slab and to a roof diaphragm, and the curved arrows that you see on the roof diaphragm illustrate the flow of forces along the diaphragm to the shear walls. The shear walls are the walls that act parallel to the direction of applied lateral load. The bond beams, the areas at the top of the walls, transfer reactions from the walls to the horizontal diaphragm, and they also act as diaphragm cords. So let's look more closely at that building again, and we can see the diaphragm. If we can zoom in a little bit, please, on the picture of the building, you can see that what we've got is a roof diaphragm that takes resists reactions from those vertical strips, transfers them to shear walls, but the diaphragm is also acting as a member in a horizontal plane. Okay. I really want to focus with you for just a minute more on the role of the diaphragm, because it's really important, and understanding the role of the diaphragm will help you understand part of the flow of the design process in the direct design method. If we were to look at this building from the top, we would see a single rectangle. That's the diaphragm. If this building were part of a multi-unit commercial center, for example, we might see a number of diaphragms representing different units or modules, and each of those diaphragms would resist loads, would take loads transferred to it by out-of-plane strips, and would transfer those loads to shear walls. In the case that we're looking at here, the shear wall on your right, that's shaded a little bit darker in gray, has to resist the loads transferred in its plane from one diaphragm only. In a general case, we might have loads from a diaphragm on the other side only. Finally, notice that the size or the span of the diaphragm that we have on each side of the shear wall tells us how much vertical load can be brought into the shear wall. Okay, we've used this slide about all we can. Now let's talk a little bit about precisely how we design the strips perpendicular and parallel. The strips perpendicular will resist moments that come from eccentricity of applied gravity load, and we can denote those as a triangular moment diagram, because remember that the strips are simply supported top and bottom. Then we have, in addition to those, moments from wind loads, and those moments can act either in or out depending on the direction of the wind. We sum those, and for design purposes it's perfectly reasonable for us to assume that the maximum moment will occur somewhere near the mid-height of one of those strips. So the design of that strip is a comparison of the combination of factored moments and axial loads with an interaction diagram. If we were doing the design by hand, we'd have to generate that diagram by hand or by spreadsheet. The direct design method does this automatically for us in a way that's transparent to us. If the orange dot is inside the blue line, we're fine. Design of parallel walls is done in a similar way. The combinations of axial load, shear, and the height above the foundation at which that shear comes in, the diaphragm level, will give us moments. we have to design that shear wall for moments in its own plane. And again, that's done by comparing factored design axial loads and moments with an interaction diagram. The direct design method does that automatically. We check shear capacity by looking at the equations for shear capacity that come from the MSJC standard. If we were doing this by hand, the designer would do this calculation. If we're doing it with the direct design method, it's embedded in tables that the designer uses. And our shearing resistance is achieved by ensuring that we have sufficient length of shear walls in the plane where load is applied. So all of these concepts are going to be underscored again when we study the application of the direct design method. Lintels are very simple. They're simply supported. We have to design them for moment and for shear. Moment for a simply supported beam is WL squared over 8. Shear is WL over 2. And our shear design is as simple as you can possibly get. We want to make sure that the lintel is deep enough so that we don't need shear reinforcement, because it's usually difficult to install. Flexural design is accomplished by making sure that we have enough reinforcement so that that reinforcement, acting at yield times an internal lever arm, equals our moment. We distribute shears to shear walls by the classical approach that's associated with a flexible diaphragm. The shears are distributed in accordance with tributary area. If you can imagine that the shear wall that you're seeing on the screen to my right, shaded in gray, that shear wall would be responsible for loads that were brought in from the right half of the diaphragm that is connected to it and is associated with it. If we had another building on the right-hand side of your screen also connected to that shear wall, then the shear wall would be responsible for loads coming in from both diaphragms. So let's sum up what we have so far. The direct design method is a simple way to follow these steps. It works for many kinds of masonry buildings. It focuses on a basic layout of reinforcement that I've already discussed in general terms with you, and I'm going to show you in specific terms. And it addresses exactly the same things that a designer would consider in a very systematic fashion. This is useful for somebody who has to transfer from one material to another, or is looking at masonry after a time away from it, or even for an experienced designer who wants to make sure that he or she hasn't forgotten something. The tables are in the Direct Design Handbook. You can see that I've got a lot of information in front of you at a font that is so small that you can't possibly read it. And that's the point. You don't have to read it from here. We're going to go through the steps. The little picture that I've shown you on the left of your screen is the cover. The one in the middle is a foreword to the handbook. And what it shows you, it's a one-page guidebook, how to go through each step. And it shows you exactly where to look in terms of standard, mandatory language, and where to look in terms of commentary. But it's a good starting point. Okay? Whenever I start to do a design with the Direct Design Handbook, and I haven't done it in a while, I'll always turn to this page. And finally on the right-hand side of the screen that you can see to my right is one of the many tables. Okay? We're not going to focus on getting individual numbers from those tables. Okay? We're going to focus on what you go into each set of tables with and what you come out. Let's talk a little bit about the designations of typical reinforcement in the direct design method. And here I'd like to go step by step. What we're looking at is an elevation of a masonry wall. And you can tell that it's a masonry wall because I've put in some concrete masonry units in the lower right-hand side. Okay? And I hope everybody can see them. Then we have some openings. Above those openings, okay, we have regions of masonry that are uncoupled from the rest of the wall via control joints. And so if I could focus your attention, please, on the opening on the left, you can see that proceeding upwards from the left and right hand upper corners of that opening, we have a control joint with a dog leg in it. The control joint does not begin directly at the jamb, but rather a prescribed distance away from the vertical line of the jamb. So that area is resting, as it were, on the masonry on both sides of the opening. Within the masonry above each opening, we have bars at the bottom, which are denoted with the B. That's the B as in Bravo that you see. We have edge bars that proceed vertically. Now let's look at the rest of the wall away from the opening. Away from the opening, you can see that we have at regular intervals horizontal bars. And from our previous discussion, you can imagine that what those horizontal bars are doing is resisting moments, okay, that are acting, that are tending to bend that wall about about vertical lines. Okay? So those H bars are resisting flexure in a horizontal plane, out of plane flexure for that wall. Then we have some V bars that are going vertically, and those resist bending moments for the vertical strips that you saw. We have C bars. Those are our chord bars that are helping tie the roof diaphragm into the walls and also act as roof diaphragm chords. I'll be discussing each kind with you. Finally, before we leave this picture, I'd like to zoom in on the opening at the lower left, and I'd like to show you the J bars. These are very important. These go from the foundation, and you can see the splice at the bottom, from the foundation, and they connect the masonry above the opening to the foundation. We need this because something has to give us a positive connection to the foundation to protect our structure against wind uplift. Good. So we'll be referring to these designations of typical reinforcement as we go along. The basic steps of the direct design method, 12 steps. Don't try to read this slide. These are the steps that are taken directly from the foreword, directly from the one-page guide. We're going to get basic information from ASCE 7, verified site conditions, obtain our seismic design category, pick a lateral force resisting system, and then identify those diaphragms that I was telling you about. We're going to pretend like we were a bird, and we're going to look down at the top of the building and identify the diaphragms, because those diaphragms unify walls that are loaded out of plane and walls that are loaded in plane. We're going to calculate through the magic of the direct design method. We're going to calculate how loads are brought into those diaphragms and how those diaphragms transfer loads to shear walls. Then we're going to go through each of the bars that I've told you about in general terms in the first part of this presentation, and then in specific terms in the diagram that I showed you with the different types of bars. We'll detail the J bars. In the places where we have headers or masonry over openings, we're going to detail the V bars. We'll do the B bars. We'll do each other kind. We'll make sure that the information we need is specified, is provided on the construction documents, is provided in the specifications in the construction documents, and that we have the required details shown on the construction documents. So if the designer goes through these steps, he or she will have finished the mission. So let's apply this to a very simple building. For purposes of this presentation, the building has been described as a dentist's clinic in Rockwall, Texas. I always thought when I looked at it that it would be suitable for use as a garage or a stable, but who knows? Here's what's important about the building. The walls that you're looking at that are gable walls that'll be considered to be on the left and the right when we start doing the design, those walls have no openings. The only openings in the building are in the front wall that you can see, 3 openings, and you can't see the back wall, but it has identical openings, and the wall that's hidden is also a gable wall. So we're going to be designing a very simple building. It will have one diaphragm only. One set of walls, gable walls, will have no openings, and the other walls will have openings at the front and back. And for purposes of this presentation, we can presume that it's a dentist's clinic. So, what I'm going to be doing in the remaining slides is going through exactly what we do for each of the steps that I showed you before. These steps are numbered identically with the way that they're numbered in the Direct Design Handbook. We get information from ASCE 7, okay, our load standard. We get the occupancy category, which is in our case is an occupancy category 2. Our ground snow load, mapped ground snow load, 5 pounds per square foot. Our 3-second gust basic wind speed is 90 miles an hour, exposure category B, and our short period and 1-second period spectral response accelerations are 12% G and 5% G. You'll notice that these lie within the limitations that Jason discussed with us earlier. We verify next our site conditions and architectural aspects. We don't have any unusual or extreme loads. Okay? We have 1 story only, rectangular diaphragms, masonry walls on all 4 sides. Okay? We don't have unusual configurations of penetrations and openings, and our parapet height is within limits. So you can imagine that since this is our example, that all of the requirements would be satisfied, and indeed they are. Next thing we do is obtain the seismic design category. Given S1 and SS and the occupancy category, we get the seismic design category from table 3.2-1 of the handbook. And in our case, for these values, the structure is assigned to seismic design category B as in Bravo. Based on that seismic design category, we have a choice of lateral force resisting systems. Okay? Our options are an ordinary plain masonry shear wall, ordinary reinforced, or special reinforced. And let's review those designations a little bit. We talk about plain versus reinforced, and this refers to design intent. In a plain masonry wall, masonry is assumed to resist flexural tension. In a reinforced masonry wall, we neglect the resistance of the masonry and flexural tension, and all flexural tension is assumed to be resisted by reinforcement. So that's the first decision we have to make. Will a lateral force resisting system be composed of plain or reinforced walls? And finally, the level of detailing. And our 2 choices for this are ordinary and special. We're going to choose a low level of prescriptive detailing, and this corresponds to an ordinary reinforced masonry shear wall. So that's what we're going to use. Here's how the direct design method uses that information. It knows that there are certain prescriptive spacing limits for different levels of detailing. So the choices that it gives us will automatically meet that. If we go to a higher level of prescriptive detailing, our seismic forces for design can go down. And the method also knows that. Now let's divide the roof into diaphragms. Okay. We've done that. We have 1 diaphragm. This is very simple. If we had a multi-unit commercial center, we would divide it up into different diaphragms. And if we had a very long length of walls, we might have to divide into sub-diaphragms, as Jason said. So then we compute our design lateral force for wind and seismic. We will check the reinforcement for out-of-plane wind and out-of-plane seismic. So you can imagine that what we're doing is we're getting vertical reinforcement in those strips that I showed you before, and also some corresponding horizontal reinforcement. Then we'll do the same thing for in-plane requirements. What happens when the walls act as shear walls? We'll check diaphragm chords, we'll check the lintels or headers, and then miscellaneous. In our case, it's quite simple. We have one diaphragm, and joists bear only on the north and south walls, the ones that have those openings. There's openings also only in the north and south walls. And I'll point out the differences that these make and the fundamental reasons for that as we proceed. So the first thing we're going to do is design this building in the north-south direction. And what I'd like you to do with me, okay, is imagine that we're looking at the side of the building that has these openings. In the north-south direction, I'll calculate a base shear from wind as a vertical projected area times a wind coefficient that the method calculates for me, and I'll do a similar thing for seismic based on the building's mass or weight. It turns out that seismic governs. I go into the out-of-plane tables, 3.2-5 and 3.2-6. The walls, okay, if I have no joists, okay, for the walls that are going in the north-south direction, because remember the joists always go just parallel to those, I find out that I need number 5 vertical bars at 72 inches and number 5 horizontals at 120. So far, so good. The no joist choice is used within the direct design method to emphasize that those walls don't have beneficial compressive load on them. I continue in the north-south direction. I have to check on the length of the wall that I need. Okay? Remember that shears are resisted by length of wall. I check the length that I need for shear, and it's 3.5 feet. I check the length that I need for flexure, and it's 5.2 feet. That governs. This is a really interesting calculation. A lot of work is going on underneath, because the direct design method is checking how capacity might be governed by shear or how it might be governed by flexure. The greatest length of shear wall that I need is 5.2 feet. I have 40 feet, those gable walls in the north-south direction, so I'm okay. I'm going to do diaphragm chords and miscellaneous stuff later. Okay. So let's look where I am. In plane requirements, I've got that figured out. I've got the length. Okay. I need for my diaphragm chords one course with 2 number 5 C-bars at the diaphragm level. Okay. I don't have any lintels, no openings, okay, to worry about for those walls. Now let's go look at the east-west direction. I do the same calculations there. Okay. I calculate wind load, I calculate seismic load, and I find out here that seismic governs. So again, okay, for loading the building in the east-west direction, okay, I calculate what I need. Here I have joists bearing. I take that into account. I have number 5 vertical bars at 120 inches and horizontal bars at 120 inches. Okay. I check the length of walls that I have for in-plane requirements. Okay. For shear, I need 3.8 feet. For flexure, I need 4.5 feet. I get to add up the lengths that I have for each segment. I have 4 8-foot segments. Those add to 32 feet, much greater than the 4.5 feet that I have, and I'm fine. For diaphragm, again, 1 course, 2 number 5 C-bars at the diaphragm level. Okay, so now we'll do some miscellaneous stuff. I check the table that the 1 page forward tells me to check, and I don't need any O-bars. I check if any diaphragms share a common shear wall line. In that case, I don't have any. I only have 1 diaphragm, so I don't have to do any of the additional checks that would require. Now I have to detail the J-bars in each segment. This is important because the J-bars are what hold my headers and my roof down against uplift. I need these in every segment that has overlying headers. I've chosen a way to do this that's graphical. Each segment in these walls with openings is 8 feet long. And you can see that in the bottom line, I've got underlines. Each underline indicates a cell. So in the very left-hand cell, I have an E, an edge, and a J, a jam bar. Okay? Then I have an open cell and a V bar, 1, 2, 3, 4, 5 open cells, another V bar, and so forth. So this is showing you schematically where the bars have to go. I do the same thing for V bars in each 9-foot 4-inch header, again using each segment to indicate an 8-inch cell. Next, I have to detail the lintels. Okay? The lintels have to be, in accordance with Table 3.2-10, fully grouted, 24 inches deep, 8-inch bearing at each end, and 2 number 5 bars, B bars, bottom and top courses. I need no O bars. So let's sum up. It's a simple way to design many masonry buildings. It focuses on the basic layout of reinforcement that we saw in a schematic way in the beginning, and then in a detailed way in the second portion of the application. It addresses the same things that a designer would have to consider in a very organized, systematic way with tables to make things easier and make sure that a designer hasn't overlooked anything. And in all of this, the direct design method is a helpful, user-friendly design aid. Thanks very much for your attention.
The design example, which Rich just presented, illustrates the procedure for the Direct Design Handbook. This procedure, in reality, is applicable to much more complicated structures, though, including structures with multiple rectangular diaphragms, multiple roof elevations, parapets, veneers, different roof pitches. It includes the effects of rooftop units. And in addition to these features in the current draft, the TMS Design Practices Committee has already begun work on the next version of TMS 403, which will engage changes that are in the next edition of the MSJC standard, as well as new features to the document, incorporating desirable features such as different wall thicknesses, different bar types, different mortar types, and other features. TMS 403, Direct Design Handbook for Masonry Structures, is a quick and easy method which provides safe and economical designs. The 2012 IBC and the 2012 IRC both permit use of the TMS 403. The method provides final designs for a narrow range of structures that are very common in the United States. And when you walk outside of that range for some applications, TMS 403 is still very useful as a preliminary design guide or for partial designs. The method takes you directly from what you know to what you need to know. TMS 403 was created for you. Your own copy of TMS 403 can be purchased from the Masonry Society online at www.masonrysociety.org. We know your time is valuable. Think how much time TMS 403 might save you, and compare the savings of time to the cost of the handbook. At a young engineer's billable rate, the cost of the document is less than half an hour. We appreciate your time today listening to this 1-hour basic introduction to the TMS 403 standard. If you'd like to find or schedule a more in-depth half-day or full-day seminar explaining how to use the handbook, please contact TMS.